Now, Huntington's disease is a devastating condition, and science isn't really in the business of ascribing terms like evil to things, but there's very little good to be said about a disorder that slowly robs someone of their physical and cognitive abilities. And yet, ironically, it may now be that within the faulty gene that causes Huntington's lies the power to tackle our greatest foe, cancer. Marcus Ernst Peter is a professor of medicine at Northwestern University. He joins me now to tell us more. Marcus, perhaps you might bring us back in time to the very beginnings of cancer and multicellular life, because our understanding is that cancer must have been around a very long time, and our ways of fighting it are newer than perhaps people may realize.
You're absolutely right. It is really about the history of both of how we treat cancer as well as how nature dealt with the problem. You're right. It's absolutely ancient, and we started treating cancer just about around 100 years ago. And of course, cancer is probably a billion years old or older, as old as multicellular organisms. So I think let's first look at the way that traditionally we've been treating cancer. I mean, like any disease, a sick patient shows up at the doctor's office ever since we had doctors and said, something's wrong with me, make me healthy again, right? And so then the doctor basically compares normal to disease situation.
Yeah.
And say, well, how can we fix you and bring you back to the normal state and make you healthy again? So that's been traditionally the approach. The problem with cancer is that doesn't work that well, because by the time you show up at the doctor's office with symptoms, your cancer is so advanced that it's just not one rogue cell anymore. There are millions of differences in these tumors that you have, that you may have, and the problem is now to tackle all of them at the same time and to make that normal again is close to impossible. We try to approach it with precision medicine and sequencing all cancers on all people, but I'm not so sure whether we're going to be ultimately successful with that.
Are you saying that by the time someone presents with any symptoms of cancer, not only are the number of cancer cells in their body huge, but also the range of types of cancer cells within their body are very different too? Because people think of cancer as being a single thing, but actually it's sort of a wide range of sort of species of cells, right?
Well, I think that is the perception at the moment, but in reality, my view is, and that is why I'm trying to leapfrog all of this, it is actually just one disease. It is a disease of your genome. There's something wrong in your genes that goes rogue, and that is at the bottom, at the basis of all cancers. It is intrinsically a disease of increased mutations and genomic instability, and there is not a single cancer that doesn't fall into this category. So the idea was maybe nature developed something over eons of evolution that detects just that. When is the mutation rate above the background level that we all need for evolution to occur, right? And so are there systems that allow nature to eliminate a cell at that moment? And you have to understand that the understanding is that pretty much all cancers can arise from a single cell going rogue. One mutation at the wrong time in the wrong place, and you basically are dead. Now, one thing, in addition information I need to give you, is the system that we believe could be behind this mechanism that detects and may be eliminating cancerous cells, and that is the system of RNA interference. So we all have about 20,000 genes. Those are the information pieces in every one of our cells, right? And genes basically get converted to proteins that do most of the functions in a cell. And in between proteins and genes, we have what we call RNA.
The key to your research is that RNA. Will you sort of break down what exactly RNA is before we go any further?
Absolutely. We have about 20,000 genes in our genome, and they all consist of a code that is comprised of only 4 letters, G, C, A, and T. So it's a very simple but very long code in every one of our cells. And this code then gets used to produce proteins, which are basically make every cell work. That's what makes all cells work. In order to get from the DNA, which is a long string of all of this code, G, C, A, and T, it gets translated to a middleman, and that we call this RNA. And that is the same 4 letters, slightly different, that are translated from the DNA that give rise then to protein. Okay?
Right.
So now the issue is that that it was found in the early 90s that short pieces of RNA, when you stick them into any cell, it could be animal cell or even plant cells, they will attack the gene or the RNA they derived from with the same sequence. We call this RNA interference, or RNAi. In 1990, some plant scientists tried to increase the intensity of the color of a certain flower. And so they put a gene that basically makes the color into the flower, expecting the flower now to have a deeper purple rather than a light purple, right?
Right.
And the stunning result was that the flower had no color anymore. They found that the gene that they put into that plant was converted to an RNA, and that RNA was broken down to small pieces and targeted the very gene that they wanted to enhance in there. And that resulted in the loss of the gene. So it was the opposite of what they actually planned to do. This is how RNAi was discovered.
So essentially, inserting RNA is like introducing a killer twin, and you basically wipe out either side of RNA by introducing it into a cell.
Yes, but in most cases, of course, our goal is not to kill anything. Our goal is to study gene functions. So we want to take one gene out so it doesn't function anymore, and then just study how the cells respond, how they behave, right? But of course, the flip side of it is you could use this to kill cells. And sometime in the fall of last year, we found a whole class of small RNAs that had this function. They were highly toxic to cells, and it turns out mostly cancer cells.
So to recap, we have cancer that developed a long, long time ago, and we had multicellular organisms. And these multicellular organisms developed this RNA killer twin mechanism to stop cancer initially. But
no, nature developed this to regulate a gene expression. So usually the purpose, that's how we scientists have been viewing it, is not to kill anything, but just to change the expression of certain proteins in cells. But it turned out that you can use it to kill cells, and we found a class of RNAs last year that allow us to do it. And it was surprisingly cancer-specific. Normal cells were not affected by it. And so once we realized that, and it's really a concept that we're developing, has nature developed a system that is based on this RNAi effect to eliminate or suppress cancer at the moment it arises in the body? And so that's when we started looking for, is there any disease out there that has to have three criteria? First, it must be characterized by the loss of certain tissues. Second, there's got to be an RNA component. And third, the most important part, do these patients have reduced cancer load? Because if we're right, then this mechanism is an anti-cancer mechanism, and while you may have a devastating disease, on the flip side, you may have less cancer.
And so you were looking for something that behaved in the same way that could potentially cause this self-destruct mechanism in cells, and you came across Huntington's.
Yes. We found that Huntington contains, the disease gene contains sequences that have this activity that we discovered last year, and when we take these pieces of sequence and introduce them into cancer cells, they all died. And we test this in a preclinical mouse model, as we say, of human ovarian cancer in mice. And we delivered these small pieces of RNA using a special type of nanoparticles. RNA molecules are rather large. They don't enter cells that easily. You have to help a little. And nanoparticles are a good tool to deliver the RNAs to the cells in the body.
So you're essentially using the mechanism that Huntington's uses to attack the cell and cause cognitive decline in people to actually cause that sort of self-destruct in cancer. Absolutely.
And of course, the $20,000 question is, of course, why are we not inducing or causing the symptoms that Huntington's patients have when we introduce these sequences? And we believe that those sequences are not very toxic to normal cells. It may sound strange, given the pathology in these or the symptoms of these patients, but you have to consider that Huntington patients usually don't get sick before the age of 40. The earliest onset is 30 to 40 years, and before that, they have these sequences in pretty much all the cells in their body, in all their cells, for decades without any symptoms or very little symptoms. So in reality, it's not very toxic. However, when we take the very same sequences and put them into cancer cells, they're blown to pieces in a very short period of time at very, very small quantities. So what we're hoping of course, is that in doing a cancer treatment, and that's what we found in the mice actually, is that the treatment that we only do for a few days may be tolerable. So the brain cells are not affected that much because they are normal cells and they are quite resistant. It's just when you're exposed to this for 40 years, you lose some cells. Unfortunately, it's only a very specific subset of cells that are affected. And of course, since it's in the brain, it has a fundamental effect on the entire body of these poor patients.
So how do we make sure that we don't kill healthy cells? And how does this this RNA know what a healthy cell is versus a cancerous cell?
Well, let's put it this way. In this case, we don't need to target. Most people try the approach to specifically target a cancer cell, which is very difficult again because they're all so different, right? Coming back to the original problem. Our approach seems to work by introducing this RNA into every cell in the body. So the question is exactly why are normal cells not affected? And we believe we have a couple of ideas how that happens, and it's in the RNA again. So there are in normal cells, there are similar types of RNA that act like protectors of normal cells. And it's been known now for more than 13 years that this type of protector RNA, that this is actually really downregulated in all cancers.
Okay.
So there you have it. The protector RNA is down. Now the cancers are much more susceptible to the toxicity of these RNAs we introduce. In normal cells, we hope, will be sufficiently protected by the protector RNA.
So what's the next step for your research? How do you get this to develop to clinical trials?
Of course. I mean, that is the ultimate goal. And there are two steps. First, we need to increase the efficacy of the RNA that we use. And we also need to increase its stability. RNA is also known when you put it into the bloodstream of a patient that it gets actually removed, degraded quite quickly. And of course, on the other side, most importantly, there is some technology development that needs to be done now to improve the delivery. And at the moment, we're using artificial nanoparticles developed by people. Again, in this case, I'd rather prefer to follow nature again. Normal cells communicate with other cells, including cancer cells, with little nanoparticles of their own. We call them exosomes. And they can transfer RNA from cell to cell. So I think what needs to be done next, or what I would like to do, is to find a way or work with people who already developed this, take these natural nanoparticles that cells communicate with, load them with our toxic RNA molecules, and then start treating. And I'm sure you're going to be asking me about the timeline. As I said, we are trying to develop a completely new concept. It could go rather quickly in the next 3 to 5 years. It could also take much longer. So at the moment, it's a concept stage. It looks rather promising, but there's still a lot of development that needs to be done before we get this into the clinic.
There are a lot of people researching cancer from many different angles and some really interesting studies, even just in the last number of weeks, showing great promise. Do you think that 2050 will be a year without cancer, or do you think we will ever fully cure humans from cancer?
Well, to be honest, this prediction has been made so many times, and it's always been wrong, and the opponent is such a formidable one. We always underestimated what we're up against. That's very hard to say. But my personal opinion is yes, by 2050, I think we will be able to cure most cancers. And early signs are already visible. You may have heard about all these, all the rave right now is immune checkpoint therapy, immune therapy, right? You may have had it on the program already. And that, I think, is working for the same reason that I believe we have some chance of getting somewhere with this, because what they're doing is, in this treatment, is they follow nature again. They're using a mechanism like the immune system and try to direct the mechanism, improve the mechanism that nature developed over eons to kill cancer cells. And that, I believe, is the reason why it works in a certain percentage, still too low, but increasing constantly, of patients that are now fully cured, that would have died just 5 years ago. So there's a lot of hope, and so I think overall I'm quite optimistic.
Marcus Ernst Peter, Professor of Medicine at Northwestern University, thank you very much for joining us.
Thank you for having me.
Do you know, I knew very, very little about Huntington's until I was doing a talk show probably about 10 years ago now, and we talked about how will you plan for the future? And someone texted in saying that they knew they were going to die, and we put this person on the radio, and they talked about their life with Huntington's, and knowing that this was going to happen to them, and it was the most. I mean, it was the most affecting interview I'd ever done, and we ended up putting it into an awards show. We won our first award for radio for just letting this person talk and hearing what they had to say and asking the questions in the right way. But it made me really think about what we do on Earth, and it was just one of those extraordinary moments of my life. So there you go, a little personal story. Okay, time to look at your comments and emails and texts from last week. We were talking about bats and how bats seem to have the key to live forever, and if it weren't for like accidents or other stuff, that they could actually theoretically live forever. Emma Teeling, the professor from UCD, who'd done this amazing research to figure out why they're able to live so much longer than people in bat years, was giving us lots of information. Someone texted in saying, Jonathan, can bats cause cancer, seeing as they seem to be flying blobs of it? I'm not sure she said that. I don't know. That wasn't in her interview. I don't know if you read between lines and missed. I got something that I didn't, but I didn't think she said that. But there are some types of contagious cancer, and the Tasmanian devil or the Tasmanian wolf had a sort of cancer that appeared on its nose, and it used to get tumors on its nose, and it wiped out huge numbers of this animal. That was one of the few cases of recorded contagious cancer, but generally cancer cannot be transferred from one person to another. Bats can do, they can jump different diseases, as we know from SARS, but not cancer. Rabies and SARS, and also vampirism. Another says, hey, did the people in zoos not notice their bats were long-lived? Great show, by the way, today. Well, it's not that they live, it's not like they live for generations and generations, but they do live a lot longer than people. It's just, I get maybe unless you're thinking about it in bat years and you're aware of the longitude of other animals relative to their size, you might not have noticed that. Also, maybe people in zoos, in the 60s and 70s just didn't examine the bats that much. I don't know. Yeah, maybe they died in accidents, or malnutrition or being caged, and that's not fun, is it? We were also talking about smart pills and brain stimulation via electrical current to make yourself smarter in a short period of time, which of course kicked off a big conversation on Twitter about how this is really early stuff and it's not really very convincing, and neuroscientists say there's a great way to get smarter, and that is reading books in education, which of course, but I guess those sort of quick fix stories are interesting to talk about, particularly if there are embryonic signs of a potential there. We got an email in from someone saying, really interested in your discussion on smart pills, particularly thinking about their application for people with ADHD. My son has been diagnosed with mild ADHD and mild Asperger's, and we wouldn't have ever dreamt of medicating for it. But your conversation about smart pills makes me wonder, is there a beneficial application here? Not sure that's what we wanted to do. And I don't think self-prescribing for conditions is a good idea. Which is one of the worries that I guess when you cover this sort of thing is that people go, oh, what about with this? And we heard last week about people self-medicating fecal transplants. That's a dangerous thing to do. Don't do that. Like, we had a conversation about this before we went on air, didn't we, Aidan? And I was like, I was worried about people doing this. I don't think until you see good, strong evidence and doctors prescribing medicine for a particular condition that this is something you should do, to be honest. Yeah, and as they always say in these sort of situations, your doctor or your medical health professional are the people you need to go to, because early stage research, science, even scientists coming out and saying, this is it. There's still a whole load of stuff that happens from the discovery in a vial to it being a marketable, safe medicine that isn't toxic in small amounts and so on and so forth. So you just can't jump the Q in that way because it could lead to serious consequences. And as I say, there was a huge amount of discussion about IQ and where IQ sat in terms of gauging people's intelligence as well. Do follow us on Twitter at Newstalk Science, particularly if you're listening from 12 to 1 where the programme is live. There's always these sidebar conversations that often very smart people are having about how we're getting shit wrong. And, that's interesting in and of itself. That's it from us for this week. Hope you enjoyed the podcast. If you did, tell people about it. We do sincerely mean that. I don't just say that. I really would like you to text someone or email someone and say, you like this. It would help us. Thanks to Jen Largan, who was researching, Aidan McKelvey, who was producing, Peter Malloy, who was on sound. We'll be back next Saturday with more Futureproof from 12. In the meantime, stay curious.
Futureproof on Newstalk.
Proudly supported by Science Foundation Ireland. #BelieveInScience.